Okay, so let's do another example of integration using trigonometric substitution, aka integration by trig sub. Here are the forms we want to look out for. So again, we've got the square root of a squared minus u squared. So this is constant stuff, this is variable stuff. This is the substitution we make, and the reason why is once we plug that in and do some algebra, we get a Pythagorean identity that collapses our radical. So it's very handy. The understanding is that the thetas are restricted so that when I take the square root, I don't need absolute values. A second form is square root of u squared minus a squared. Again, variable stuff, constant stuff. We make the substitution because when we plug that in for u and do some algebra, we get a Pythagorean identity that collapses the radical. Again, restrictions on theta. These restrictions are just based on where, so for example, this restriction is based on where cosine, what pops out of the radical, where cosine's positive. Cosine's positive in quadrant 4 and 1, etc. That's where the restrictions are based on. So this one is based on cosine, which pops out of the radical. This one's based on tangent, which is positive in 1 and 3. And this is based on secant, right? So for this form, we make this substitution because when we do some algebra, we get a Pythagorean identity. This pops out, and so we restrict these values because secant is the flip of cosine. It's positive in quadrants 4 and 1, and strict because we don't want to divide by 0. All right, with that said, let's do an example. Okay, so let's say we've got this indefinite integral of the square root of x squared minus 7 all over x dx. And so we just want to check which of our classic forms is this in. So it looks like I've got variable stuff minus constant stuff. So that means I'm looking for a u squared minus a squared form. So that looks like this form right here. So we want to make a secant substitution. All right, so we're going to use the form u is equal to a secant of theta. So then the question is, okay, well, what's playing the role of u and what's playing the role of a? Well, if this is u squared, then u should be x. And if this is a squared, then a should be the square root of 7. So a does not have to be an integer. So this is perfectly fine. And so that's times the secant of theta. Okay, that's going to help us replace our x's, right? But we also need to replace the dx. We're going to do that by just taking the derivative. So the derivative of secant is the product of secant and tangent. Okay, both of the same angle, and then d theta. Okay, so this helps with this, and this helps with this. So that seems like a good start. All right, so in for x. Well, let's just think about this, right? So if I were to square this, what's x squared? X squared is exactly 7 secant of theta. So that's what I'm going to plug in for x squared here. Got that just by squaring this. So that gives me 7 secant of theta. That should be squared, of course, right? So minus 7. That's over x, but think about what x is. That's the square root of 7 times the secant of theta. And then dx is this quantity right here. So that is the square root of 7 times secant of theta times tangent of theta d theta. So hopefully that makes sense. So we've got some canceling that's going to occur, right? So this will cancel with this. That seems nice. So those are gone. I also noticed some algebra inside my radical, right? I can factor out, it looks like I can factor a 7 out, and then I want to be on the lookout for a Pythagorean identity. That's really the reason why we do these trig subs, is that, again, the Pythagorean identity that you arrive at by making the sub collapses the radical down. Makes life so nice. Okay, so I'm happy with that. And then I think I still have a copy of tangent here. Okay, well, this is a very famous Pythagorean identity. We know that this is equal to tangent squared. And we want to remember that we're doing these calculations with the understanding that we're choosing nice thetas where tangent's positive. So I don't need an absolute value because of that. It's a little sneaky. They mentioned that a little bit in the beginning. I remember when they cover that, but that's really what's happening. Let's see here. So yeah, the square root of 7 is right here. And then this is going to be the square root of tangent. Again, with the understanding that we're choosing nice thetas times tangent from before, d theta. So of course I can factor out that radical 7, right? So this is going to give me, it looks like tan squared of theta, d theta. Okay, so that seems pretty good. As it stands, there's not much I can do with that. So it might be wise to use a Pythagorean identity. And again, let me just remind you that just one more time. It's so classic, so useful, so nice. Okay, so I can replace tangent squared with secant squared of theta minus 1. Let's go ahead and do that. Okay, so that's a d theta. That seems pretty good. And that's pretty nice if you think about it, because we know the antiderivative of secant squared, and we certainly know the antiderivative of 1. So this is really nice. I think the worst is over. So yeah, the antiderivative of secant squared, so there's tangent, so tan of theta. Antiderivative of 1 is theta, okay, plus c. And then we have to remember, how do we go back to the land of x's, right? So I started with x's. I can't stop now. I got to go back to x's. The key to go back to x's is we need that right triangle, and we get that from our original substitution statement. So we need a right triangle. So let's go back here. X is equal to radical 7 secant of theta. Get the trig function by itself. You want to isolate it. Divide out that radical 7. Don't worry about rationalizing. This is fine. Okay, so now we fill in the right triangle. Don't be scared of secant. It's just the flip of cosine. So just instead of doing adjacent over hypotenuse, you do hypotenuse over adjacent. Okay, and we can use the Pythagorean theorem to find the missing side. So that seems nice. So what do we have for that? So that's going to be a squared plus the square root of 7 squared equals x squared. And we'll just solve for a. So that means that a squared is equal to x squared minus 7. So a is positive x squared minus 7. That's not so bad. So now, well, we want to be careful though, because this helps us with the tangent, right? But with theta, we want to be careful. So let's take care of the tangent, and then we'll talk theta business. So tangent is opposite over adjacent. So you can either stack your radicals, or you can write them as one big radical. Both is acceptable. Okay, theta time. So go back here and just ask yourself, what's the function that undoes secant? So how do I undo this? Well, I want the inverse. So I take the arc or inverse secant of both sides. Okay, don't let that scare you. It's perfectly fine. Okay, remember when you compose a function with its inverse, those will cancel, and now everyone's happy. And so theta is exactly the arc secant of x over radical 7. Another representation for that would be the arc cosine of radical 7 over x. You can convince yourself by working with this that's true if you need to. And that's going to be plus c. So not too bad on that one. Not too bad at all.